So our first figure is Joab Winkler, and it tells us about new methods for computing roots of polynomials.
Right, thanks very much. I'd like to thank Alan and Bill for inviting me here. I must say I'm a numerical analyst, so a lot of my work is computational, and of course here it's been quite theoretical. We've talked about polynomials, graph polynomials, flow polynomials, and what I want to talk about is, well, how do you compute the roots of these things? Now you think, okay, that's a fairly standard problem. You can pick any first year undergrad maths books and you'll find methods that will do it. But it doesn't take too much work and to break those methods extremely easily. And I'm not talking about esoteric polynomials of degree 34 million. You can get it pretty low degree, even 4, 5, 6 degree, with coefficients say between -10 and +10, and those root solvers will break. Okay, so what I really want to do is to show you the new ways of thinking about computing polynomials. And I'm going to provide more of a motivational talk from a high level so that you can understand conceptually what's happening. I don't want to get involved too much in mathematical detail because that involves a lot of things on structured matrices, least squares equality problems and stuff like that, which is a subject unto itself. So here's the outline of my talk. First thing, I'm going to talk the difficulties of computing polynomial roots. And I'm just going to give you a couple of examples, simple MATLAB, why things can go badly wrong. And then I'm going to use that to try and understand why things go badly wrong and how you can then impose those reasons in a root finder. So we're going to look at the causes by using looking at the geometry of ill-conditioned polynomials. And then going to use look at a very simple root finder. And that root finder will be great in a symbolic environment. But to translate that root finder from a symbolic environment to a floating point environment with polynomials with inexact coefficients is a minefield. It's really difficult. Now, I must say at this point, I notice a lot of your coefficients are integers. I'm going to assume ordinary floating point numbers and their errors. Okay, so it's slightly more general, but what I'm going to show on the examples is even integer coefficients can cause you bad problems.
But are you telling us that if we have a polynomial with integer coefficients, then we can stop listening after part 3 because you will already give us a great algorithm?
After part 3? What? After the simple part? No, because of round-off error. What about round-off error?
No, but if we have a polynomial with integer coefficients.
And what about round-off error?
Then can your polynomial root finder do the calculation in exact rational arithmetic?
I'm not going to work in. I'm only going to work in floating point arithmetic because I'm saying I'm not going to use anything symbolic because generally symbolic stuff, if you keep rational stuff, etc., is far too slow. Everything's going to be done numerically. That's what.
And once you start trying to find the roots, the fact that the original polynomial had integer coefficients won't help you.
I make no assumptions about the fact that the coefficients are integers. So I've got a general AI x to the I, where AI is an arbitrary floating point.
I know, but since our applications will have AI.
It doesn't make any. Well, let me give you a couple of examples with integers, and you'll see one example where you'll see that even integer coefficients just causes worse than a mess. Okay? Let's just. Right. Now, there are a huge number of methods for solving polynomial questions. I've listed them, which all related after people. I should have put Newton first, actually. Never mind. Oh, but then it's alphabetical order, so that's my excuse. Bairstow, Grafe, Jenkins, Traub, Laguerre, Müller, Newton, etc., etc. And generally speaking, these algorithms work well. If, for example, the polynomials of moderate degree, the roots are simple, and the roots are well separated. This is a problem. This is one phenomenon that's often ignored. Roots should be well separated. As roots get together, they become ill-conditioned, okay? And though it has exceptions, this, I don't know if you're familiar with this, is the Wilkinson polynomial after James Wilkinson. You try putting that into MATLAB, it won't get the right answers. by a long way, okay? So those 3 bullet points I put there, they're heuristics, easy to break, but as a rough guiding rule, those are the problems. Those are going to cause you problems, okay?
Last problem has to do with the
Pardon?
form in which
Pardon?
with the form in which you put this polynomial into.
You're talking about the basis.
Well, if you put it in the usual power basis, then
Yes, I agree. If you
you're
put it in the
trouble.
Bernstein basis, sure, if you put it in the Bernstein basis, it's great between 0 and 1. But the problem with that is that the transformation between the bases is invariably ill-conditioned. So, you've gone through an ill-conditioned process to transfer it. And the trouble is, although Bernstein basis, you're interested between 0 and 1, that's exactly when the transformation is ill-conditioned. I agree with you. Okay. Notice this maybe answer Alan's question. I've taken that simple polynomial, degree 4, root of multiplicity 1, of multiplicity 4, x equals 1, and MATLAB's done a pretty bad job for me. Now, if you think about it, this is a disaster because I've only got round-off error. Round-off error is 10 to the minus 16. The error is of order 10 to the minus 4. So what that tells you is an error of 10 to the minus 16 in my input has generated errors of 10 to the minus 4.
Is that because it's multiplicity 4, so you take the 4th root of the error?
I told you it's 1 over, right, okay. It gets this to do with, it's
really
basic.
Telling x minus 1 to the 4th equals epsilon, where epsilon is 10 to the minus 16.
Basically, you're familiar with condition numbers and stuff like that. Right, the condition number is basically, it's got some term here, which call it of 1. Epsilon's the 1 over the signal to noise ratio. M is the multiplicity. So if you put epsilon c, say to be 10 to the minus 16, something like that. Okay, but that's given you a bad answer. Okay, and now you take this second example, and I must say, these coefficients, again, were integers, were simply done by using the convolve function, repeated convolution of the linear factors to get the coefficients. And so this is, again, only round-off error. Notice that, where is it, this one? That root is about at x equals 6, and what we really want are the roots all there. So we aren't doing very well here.
So in that example,
So which one?
the x minus 1 to the 100,
Yes?
the coefficient of x to the 50th would be computed as an integer by MATLAB
Yeah.
as what we would call 100 choose 50.
Yeah, that's right, yes.
Yeah, okay.
Right.
That's quite a large number.
Right, but you when you evaluate it, you would do it.
But MATLAB would know that number. If I asked
We didn't get
MATLAB
any
100
warnings.
choose 50, it would actually print out a number.
Yes,
and
we
tell me you could choose.
we didn't get it. But also, or you could do it a bit more clever. You wouldn't evaluate 100 factorial divided by 50 factorial 50. You could in fact evaluate it slightly more cleverly, so that you would keep them.
There's no possibility of error in that number.
No. Okay, I mean,
Exact number.
yes. I mean, had you changed that to say x minus 1 to 50, you would have got slightly similar. Notice as well some.
I think his question is, do you first compute the polynomial as an exact integer polynomial, and only then start doing floating points?
Yes.
To find
Yes.
integers?
Yes. 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 But but you can take that down to x minus 1 to 50 or 40 or something like that if you really are worried on that sort of thing. Notice as well what that tells you. Never accept that round-off error is random. It's round-off errors are highly correlated, okay, as I think you would agree. It's often assumed that, yes?
Just a quick question. So how do you pass it to MATLAB? Do you pass it
What you do,
in power form, or do you pass it as a subroutine in this form?
what you do, you take your x minus 1 factor, gosh, I'm going to run out of time. You take your x minus 1 factor and you repeated convolution through a loop, okay? You know, you
Given to
as a
MATLAB
vector of
as
length 101. MATLAB, the roots function in MATLAB has an argument which is a vector. That vector is simply stores the coefficient.
coefficients.
It's all it is. It's exact. So
You could use the evaluation function or the root finding function passing this as a subroutine.
okay, but
And passing the derivative as a subroutine, and then see what difference it makes. I mean, just a suggestion.
passing the derivative as well.
Yeah, directly as a subroutine.
Okay, well we'll come to that in a moment.
We can take it offline.
Yeah. Okay. never accept that round of error is random. It's often thought that it is, but if anything, as you can see, it's totally unrandom, if that word exists. Oh, now, oh, sorry. Come on. Back. Right, here's some more. Now, here I took 4 polynomials, right? And there are, on the top left, we have x minus 6 all cubed times x minus 1 to the 5. And top right, I replace the x minus 6 by x minus 0.7, again cubed, x minus 0.8, x minus 0.9. So I've kept the x minus 1 to the 5 factor constant. And so you can see what's happening. The roots are getting closer, and I've added signal to noise ratio of 10 to the 7 to each coefficient, okay? And I've solved it 1,000 times. So what you have is like a scatter diagram, or what looks more like a fract. Now, no one is going to tell me that if you get that diagram, you can work out what the original polynomial is. I don't believe you can. And and there's no way. Notice as well how the roots are interfering. Can you see? If you look at the progression, do you notice how top right and bottom left, you can see that the roots are starting to interfere? Because there's a certain, if you look here, compare that bit with this bit. Compare this bit with that bit. Notice how the roots, okay? So very, very different. This is why the proximity of the roots is important. It's not just multiplicities, it's not just signal to noise ratio, it's a hell of a lot more. Okay? Now, okay, so you can see things have gone badly wrong. Okay? And those results are not necessarily related to the algorithm. MATLAB uses the QR algorithm to solve the eigenvalue problem, but you could do done using any method, and you would have had results that are similar in general detail, may have differed in the local detail. So you then have to ask yourself, well, what's gone wrong? Now, if you think about it, all these, a multiple root has certain properties that it's, if a multiple root of degree r introduces r minus 1 constraints, because you say double root, it's the first derivative, triple root, first and second. So imagine that you know, or you have prior information, or you're looking for something that you are looking for a multiple root of degree r. What you want to do is impose those r minus 1 constraints into your root solver, okay, and thus avoid the breakup of a multiple root. So suppose you've got a polynomial of degree m, so it's got m degrees of freedom, m plus 1 coefficients, but only m degrees of freedom, because we don't care about the arbitrary scalar multiplier. So if you've got a root of multiplicity r introduces r minus 1 constraint, so if a monic polynomial has degree m, then we are in fact left with m minus r plus 1 degrees of freedom, okay? So what's the geometric interpretation of that? Imagine you've got a polynomial of degree m, you've got and so imagine your coefficients lie in r, let's just deal with real coefficients to make things simple. So your coefficients lie in Rm. There's your constant, x0, x1, x squared, etc. Every point in that space represents a different polynomial. If you know the multiplicity, you're saying that your polynomial does not lie anywhere in that space. It lies in a manifold on the surface in that space. Okay? And that's the constraint that you have to impose. Okay? So that manifold is called a pejorative manifold. And the point is that if you can work out the multiplicity structure of the roots, you know the manifold in your m-dimensional space in which your polynomial lies. And in effect, you're solving your polynomial not in Rm, but on that manifold that's embedded in Rm. Okay? And that's how you take account of multiplicities. Okay? Because you can see that, I mean, if I look at, just think of Newton's iteration, you can see why things go horribly wrong. Because if you think of Newton's iteration, well, even if you fairly near your multiple root, sorry. Even if you're fairly near your multiple root, this is going to go crazy near the multiple because it's going to become very small. So this iteration will diverge, okay? So what we want to do is the first thing we have to do is identify the
It will just converge.
well, suppose you've got a triple root and you use that iteration. As you get near the iteration, your f dash of xn is going to become very, very small, won't it?
So you're talking about a problem with round-off error?
Oh no, you're just near the I mean, imagine you've got I don't know, a triple root like that. Then if you're here, this derivative is very small. So the denominator on the right-hand side of that term will go to 0. Will become very, so
Yeah, but the Newton iteration converges fine. It's just instead of
Not
getting
in-
quadratic convergence, you get linear convergence.
I don't think it'll work. Very near, it'll.
Well, just put in f of x equals x to the n, and then you.
But what
find-
happens when you get very near?
Well, I mean, if you put in f of x equals x to the n, f prime is nx to the n minus 1.
It doesn't always work computationally. People have problems with this.
Or maybe because of round-off error.
Whatever, but I mean, the thing is, I'm trying to come this, you could not just have an abstract concept called a polynomial, you've got to do something with it on one of these machines. Okay? So what we want to do is, if you can identify the multiplicity, you can identify the manifold in which it lies, and then keep your iterations, search for the roots on that manifold, okay? Now, it's called a pejorative manifold. Now, why is it called a pejorative manifold? Because if you identify the manifold in which it lies, then if you've got one point on the manifold, and you say, suppose I shift my how much work do I have to go to another point? It's a remarkably stable process. Keep it walking along a manifold is extremely stable. If I move a little point, then the polynomial doesn't change that much. If I go off the manifold, that's when I lose the multiplicity structure, so the root breaks up, and that's when it becomes horribly ill-conditioned, and that's when I have this term, okay? So what we want to do is identify the manifold, identify the multiplicity structure, identify the manifold, do all the work on the manifold, and so we will never ever have the breakup of the of the root, okay? Now, here's an example. This is, again, I'll just do it with real to keep things simple. Consider a cubic polynomial with those real roots. So I've expanded it there. Now, suppose you have prior knowledge or something or other that says that it's got one double root and one simple root. So you take that top expression and you put x naught equal to x1 not equal to x2, and that's your cubic. So the pejorative manifold that has a double root is the surface defined by, that's one coefficient in your space, the second, the third. So this is a surface with 2 degrees of freedom, and that defines your pejorative manifold, okay? And if we think of a triple root, we have that, put x naught equal n x2. So this is now a curve in R3. That's your, okay? And as we snake along the curve or walk along the surface, we're keeping the multiplicity structure, but different points on that manifold correspond to different polynomials, okay? Right.
Isn't it cheaper to just differentiate a number of times to bring it to the root of order 1? If you know the multiplicity of the root.
How are you going to work out the multiplicity?
How do I work?
How do you work out the multiplicity?
Well, you have to know the manifold, so you have to know the multiplicity.
And how do you work it out? How do you, okay, I give you a polynomial and I tell you it's got multiple roots. And how are you going to then work it out?
Well, here you are putting in information about the order of the root.
This is purely an example. I've put this example in just to give you a concept to show what is the manifold that as you impose as the number of constraints increases, in other words, the multiplicity increases, the dimension of the manifold decreases. So instead of looking at the whole of Rm, you're looking at lower dimensional entities in Rm, That's,
We have to wait and see how you're going to use it.
yes. I'm not doing well at this rate. Oh.
We should stop interrupting you, I guess.
No, it's good actually. Right. I suppose because this is quite new to, right. Now, are you familiar with condition numbers and things like that? This is just a quantitative result that shows you why things are going well. A condition number is an error measure. It's a sensitivity measure. And to give you an idea what it is very quickly, say you've on your MP3 player, you've got a little volume button, right? Now you want that if you turn the volume button through a small amount, you'd like the volume to increase slightly. And as you turn it through a bit more, the volume increases a bit more. What you don't want is to turn the volume button through a small amount and to blast your ears out. You want a small change in the input gives you a small change in the output, okay? And this is measured by a condition number. So suppose now what this says is suppose I have my, suppose I have a polynomial x minus x naught to the r, and I'm going to perturb it. But what I'm going to do, I'm going to keep it on the manifold, so I have to keep the multiplicity constant, but not the value of the root, okay? So this is going to go to my perturbed polynomial, delta x naught all to the r. Notice the multiplicity has been kept constant, so I'm still on the manifold, but I'm considering a different point on the manifold because the root has changed, okay? Then, if you then work out the condition number of that transformation, you end up with that expression, which is quite nice, okay? Point is, it's independent of the signal-to-noise ratio, okay? Here's an example. I take that x minus 1 to the r, so the condition number, so the root is x equals 1 of multiplicity r. I'm keeping on the manifold, and that condition number, that sensitivity measure, is approximately equal to 2 over r for large r, okay? Which is wonderful. So you can think, even if r is 10, I've got a really stable system here. This is exactly what I want. If you compare it with random perturbations, remember that's a structured perturbation because I have to keep on the manifold. If I'm going to allow random perturbations so I can go off the manifold and break up the root, my condition number, depending on the class of either component-wise or normalized, is inversely proportional, or it's proportional to the signal-to-noise ratio. So if typically maybe 10 to the 6, 10 to the 7, that's why things go badly wrong. It doesn't take a lot to break a root up, okay? So what we want to do is have this sort of system here. What the diagrams I showed you at the beginning were simply obtained. All the roots broke up because of these factors, epsilon c and epsilon n, which are signal-to-noise ratio, or 1 over epsilon c is a signal-to-noise ratio. You look worried. Is that a problem? No, it's just you look really worried.
Not yet.
Not yet. Oh, it'll come. Okay. So you can see geometrically what we want to do. Numerically, by keeping on the manifold, we're dealing with very nice stable systems. The moment we walk off, we sort of jump off the manifold, we get to, oops, wrong one. We get to these sort of systems that we don't like. Okay. So now, I'm going to give you a very simple root finder. Great in theory, easily implemented, but what we want to do is transfer this from a symbolic environment to a floating point environment. So suppose I've got a polynomial, f of x, and I've written it in the form up here, where wi is the product of all factors of degree I. So w1 are all the linear factors. w2 is a quadratic factor. So if they've got like x minus 2 all squared, w2 is simply x minus 2, okay? And you can, okay.
WIR is the product of all the roots of multiplicity I, each one counted once.
Exactly, okay? I hope that's okay. So what you then do is you just perform a whole set of GCD, greatest common divisor computations, and I hope you can see that that we're looking that this will decrease because all these are decreasing sequences. Okay, you'll eventually hit a constant. Okay, never mind about how this is going to be done in floating point because GCDs are ill-posed, etc. Let's just worry as a thought experiment. See how? Okay.
F1 means the first derivative.
Yes. And sorry, that should have been yes. The superscript open bracket close is the derivative. Okay. So I do all that, and then I perform a sequence of polynomial divisions to get the polynomials h, and then I perform another set of polynomial. So first I perform this set of polynomial divisions. Remember the QI were the GCD calculations from the previous slide, and then I take these h's and I divide again to do another set of polynomial divisions. And you can see, for example, if I were to divide h2 by h1 by h2, I'm just left with w2. If I divide h3 by h2, I'm just left with w2. Okay? So I do one set of GCD calculations, two sets of polynomial divisions, and as a consequence, I'm just left with my wi. Okay? Right. And then you say...
GCD calculations.
Pardon?
These GCD calculations have to be done over the reals or complexes, not over just the integers. I mean,
yes.
Even though I had a polynomial with integer coefficients, I have to do these calculations.
Yes, the GCD, you could, I mean, there could be yes, they're done over, well, I've just done them over reals, but I mean, in general, you can do them over complex numbers.
But
Yeah.
not just over the integers. That's
No. Okay, right, so now, okay, then the problem, then the next thing, right, then the next thing, so we get our polynomials wi here. So by division of the h's, we get the wi's, and then the next thing we want to do is we solve these equations. So you can see what we've done. It's almost like a divide and conquer algorithm. We had this massive polynomial to solve in the first place. We don't want to solve that. Instead, we've broken it up into the sequence of a large number of low-degree polynomials. Okay? So instead of solving f of x equals 0, we solve w1 of x equals 0, w2 of x equals 0, up to w max equals 0. Why is that advantageous? They're much lower degree, and most of them will have simple roots only. So we've broken it up into a much simpler problem. Then if x naught is a root of wi of x, it is a root of multiplicity I of f of x. Okay, this method is described in detail if you look at a book by Uspensky, Theory of Equations from 1949. Okay, and conceptually, it's a very easy program to work. You just take one example and you'll see it very quickly. Now let's just have a look at the processes that were involved. We had GCD computations, polynomial division, and simple polynomial equation. Now, the GCD computation is a nightmare in floating point. You can't do it because GCDs are ill-posed. They're not ill-conditioned. Okay? So you have to be very, very careful how you're going to do them. Polynomial division, got to be careful because this amounts to a deconvolution problem that can be ill-conditioned. Solution of simple polynomial equations, that's not too bad because we said the W of I are much, much smaller, lower degree, more compact than the original ones you start off. That's why it's like a divide and conquer in a certain sense. Okay?
You're assuming that the type of polynomial you're considering has lots of multiple roots.
You do, but then you have to find the multiplicity.
No, what I'm saying...
Well, I am, because those are the ones that cause real problems, as I showed with the 3 examples at the beginning. You know those 3 examples I had?
Right, you mean...
What if the roots are sort of pretty close, but they don't have multiplicity?
Then that would come out when you work out the rank of a matrix. It'll be a full rank, which I'm now going to do. That's why I have to... Because what would happen if we go back, if you go here...
Let's say I have a polynomial degree 100 or 1,000 with integer coefficients and lots of groups of clusters of roots that are nearby but not identical. Every root is simple.
Yeah.
I mean, this method gains you nothing.
Well, that's a bit of a shame.
I mean, isn't it true?
No. Why will it gain you nothing?
Well, all the roots are simple, so the only thing you
You said this one, they are.
all the roots are simple.
Right, but how do you know the roots are simple?
Well, let's just say that they are.
Well, first thing you would have to do is to check it. And how would you check it?
But if it turns out that all the roots are simple, your method will produce W1 equals F, and all the W's, all the W.
But that at least is some information. If I give you a blind f of x.
Okay. But then once I get that information, what are you then going to do to help me find the roots?
Can we come to that?
Okay.
Thank you. Right, okay. Okay, I was supposed to start at 4, wasn't I? Yes. Right.
Fair to give you a little more time since we've been taking all your time with
Right, but that's good actually. Right. So now, again, I'm sure you saw from the examples before, which just had floating point errors, things can go badly wrong. If in addition you have inexact coefficients, which will occur in most applications, it's the applications here, I think I'm right in saying, are not, well, fairly unique, doesn't make much sense, but not far from being in that you have integer coefficients. But for practical purpose in applied math, you're actually interested in AI plus delta AI as you're being and you want to make sure that your delta AI are not going to cause all things to explode. So what we want to do is a sequence of GCD computation. That's an ill-posed problem because it's not a continuous function. So although f and x and g of x may have a non-constant GCD, my given inexact polynomials may be co-prime, or as you saw, even if I put f and g maybe have a non-constant GCD, I try and work out the GCD in floating point, and I'll show you later in a non-trivial example, they'll appear to be co-prime. Okay? So the first thing we've got to do now, to work out the degree of the GCD, in fact reduces determination of a rank of a matrix, and that's a difficult problem in numerical linear algebra. It's one of the most difficult problems. It's a very important problem, it's a difficult problem, and the reason is you're looking for an integer in a floating point environment. And furthermore, if you've got noisy data, so you've got different samples of noise, the rank is not uniquely defined. So I can do an experiment, get one result, matrix, may have one rank. Repeat the experiment, get a different noise sample, my matrix may have another rank. Both legitimate, okay? So you have to think about, is there uniqueness, which there certainly isn't, okay? Now, so we've got to, there are quite a few problems to deal with, okay? Right. In order to work out an approximate GCD, okay, so what we do, we have to use something that we do a lot in numerical. That is, we don't solve the problem that we have. We don't solve the problem with our given data. We shift the problem and consider a neighboring problem that's easier to solve. And what we have to make sure is that the difference, the error in the solution is not far. So let me just explain that. I've got f and g are not co-prime. Okay, so that's my exact data, but because of errors, I've got f plus, what notation did I use? Okay, f plus delta g plus delta g, that's co-prime. But if I have reason to believe, or I'm looking for multiple roots, this is no good to me. If g is the derivative of f, this is no good to me. Then if it's got multiple roots, they must have a non-constant GCD. So what I want to do is to take my f and I want to perturb it. I want to find another polynomial, let's call it f tilde. F tilde goes to f, let's call it z. I want to find the smallest perturbation to my given inexact polynomial so that it will have a multiple root. So I have inexact data, and I'm going to perturb it a bit more, okay? And we do this, and the question that then arises is, how big are these z's? By how much do we have to perturb our given inexact data so that when we perturb the polynomial, it does have a multiple root. This is done using, see what the next slide does. Right, this is done using, have you heard of the resultant matrices, Sylvester, Bezout, Dixon? Okay, we're going to do using the Sylvester resultant matrix. And the Sylvester resultant matrix has two important properties. The rank loss is equal to the degree of the GCD, and you can work out the coefficients of the GCD by using a QR or LU decomposition. Okay. Now, I've got an example of the Sylvester matrix, or polynomial of degree 4 for a polynomial f and its derivative. Firstly, I hope you can see it's highly structured. Okay. I've got 3 columns here and 4 columns here. These are the coefficients of f. These are the coefficients of the derivative. Notice that the derivative, the derivative is of degree 3, so there are 3 columns of f. The derivative, and then f is of degree 4, so there are 4 columns of the derivative, okay? Now that's a highly structured matrix. If I have perfect data and f has a multiple root, that will be singular and the rank loss will be equal to the degree of the GCD. With inexact data, that's going to become a full rank. So what I want to do is to shift this, find the smallest perturbation to shift this so that it becomes singular. But what I have to do is I can't just throw a random number generator at it or stuff like that. I have to preserve the structure. So my structured matrix, I would have to have A0 plus Z0, A0 plus Z0, A0 plus Z0. I have to preserve the structure. And that's why we use what's called structured matrices. Okay? So once you do all that, and that you do that, and you say, what is the smallest what is the perturbation? So that becomes singular. But then, of course, different perturbations are going to give you different ranks, and therefore different approximate GCDs. Okay? So anyway, to get into this, I mean, it's fairly non-trivial. It involves nonlinear least square, it involves least squares equality problems and QR decompositions. But if we go back to this slide, in effect, we do all these bits here using approximate GCDs using Sylvester resultant matrices. Okay? And we have to calculate the degree of the GCD, that gives us the rank. And this is non-trivial, and it's usually done using singular value decomposition. Are you familiar with that? It's sometimes called the Swiss Army knife of matrix decompositions. Okay, it's the most powerful matrix. It's called the Swiss Army knife because it's incredibly powerful. Okay, so in effect, we use the Sylvester resultant matrix to compute this. Okay, and then if we go forward, and let me just write. Here's an example. Suppose I've got, this is of f and g, and you can see those are 2 relatively unpleasant polynomials. Okay? And you can see they're GCDs of degree 5, of degree 11. Okay? Those are pretty nasty polynomials. Okay? So let's just work out, this is an example. Now, here you have to take this on trust from me. This is a matrix, this is a graph that will tell you the singularity. You know that f and g they had a GCD of degree 11, means there's a rank loss of 11 in the matrix. That's okay, you know there's a rank loss of 11. And so this is a matrix, the index of the singular value, and that is the log. That's the index, and that's the normalized ratio on the log of the singular values, okay? What you expect to be a rank loss of 11. So if we take the theoretically exact data, so we take those 2 polynomials, and all we do, we just expand them using the convolution function, put it into the Sylvester matrix, and work out the rank. Then if we look at the this blue, which is a diamond, so theoretically there's got to be a rank loss of 11, but you can see there's no sharp break in the blue diamonds, which basically tells you it's calculated as full rank. just to show you how difficult it is to compute a rank. So if you took that graph, you'd think the polynomials were co-prime, which they're clearly not. If you then add if you then add the theoretically exact data was the diamond, the square, right? When you added the noise, you got the green. Again, you think it's a full rank. But when you take, when we then calculated these z's to try and make them be coprime, we got the crosses which were red, and you notice the sharp drop here. From there, what's that? 10 to the minus 10 to 10 to the minus, in other words, we've lost 8 orders of magnitude. So that's numerically singular. It's exactly what we wanted. So this just shows that it can be done, but it does involve quite a bit of difficult work. And in effect, you have to do this for every single one of those GCD computations. Okay? Pardon?
Perhaps you should maybe, one thing we could do is you could give a quick overview of what's left.
Yeah, I'm coming to the end.
Sorry, and then we could have the next talk, and then you could...
Right, quick overview. There's my root solver. That had signal to noise ratio 10 to the 8. Okay. And further research. There's quite a bit to be done here, I must say. I must say that when we did this, we didn't actually have to know the signal to noise ratio, because what we're just about to do, submit a paper to, I think it's Science Journal of Matrix Analysis, is to estimate the rank of a matrix without knowing the signal to noise, without knowing the noise ratio, or the noise level, or the signal to noise ratio. So there's no subjective knowledge as to how high the noise is. It's all data driven. So I'm happy to finish there, which I'm sure you'd understand why. But if any of you are interested in sort of taking this further, I'd be happy to. But you see, there's quite a bit involved here. There's lots of stuff I haven't spoken about. Like, to get the Sylvester matrix, you've got to optimize some parameters which involve nonlinear structured norm. How do you calculate the rank of a matrix using maximum likelihood? What happens if your polynomial errors, if the errors in your coefficients are bounded? So your z's are saying, I can only move my zi between certain bounds. That becomes bounded least squared. So there are lots and lots of problems that you still have. Okay? So if any of you are interested and you want to take this further, and let me, anyway, thanks very much indeed, and sorry for overrunning.